In this session, I'm going to talk about survival models, wherein our intention is to come up with some kind of mathematical model or models to predict the survival function of a particular individual or a particular group of lives. What is the probability of survival? Or on the other side, what is the probability of death? Because if I'm able to understand the probability of death, then I can very well compute the probability of survival. So we are talking about a basic estimation. Whenever we talk about the probabilities of survival and all, our intention is on the basic estimation of what we call as the future lifetime of a person or future life of an individual. How do I estimate the future lifetime of a person? And of course, we all agree to that particular point. It is a complete unknown quantity in the beginning. At this moment, if I want to know by how many years this particular person is going to be alive, I have no clue on that. So that is why we talk about future lifetime being unknown. We will try to treat the future lifetime of a person as a random variable. That is the starting point behind this entire exercise. So, for any person, with that as the starting point, if I have to look at for any person, if I am interested in finding the future lifetime will denote it as a random variable. Now, if I start with a newborn baby, so if I start with a newborn baby, whose age is 0 years. Now, how many years will this baby be alive? So that is what I'm representing as a random variable t. T is a random variable which talks about the future lifetime of a newborn baby. It could be anywhere between 0 and some maximum limiting age denoted by omega, somewhere between 0 and omega. So omega could be any high number, maybe 100 or 120, depending on the lifetime of a person. It's a maximum limiting age. So beyond 120 days, a little chance that a person might be alive. So let's say that is the kind of omega we are defining. So all we are saying is the future lifetime of a person is of a newborn baby is a random variable taking values anywhere between 0 and omega. If that is the case, I define two more important functions here. What is the, what is the probability? What is the probability of death? What is the probability of What is the probability of death or the distribution function of t? So CDF, so we're denoting this as CDF, and we are denoting it as f of t, which is nothing but the probability of the t taking the value or less than, so it should be a small t inside, t of the lifetime less than or equal to t years. So this means that what is the probability that a newborn baby will be alive or will be dead before t years? So this is what we call the distribution function of t, and on the other side, the survival function means what is the probability that a person, that the newborn baby will be alive for more than t years, will be alive for at least t years. So this is nothing but 1 minus the distribution function of t. So here this is why we talk about f of t being the probability associated with the death within the t years for a newborn baby, and the s of t denoting the survival function for the newborn baby beyond t years, right? So we always use these two functions, one the survival function and two the cumulative distribution function of the future lifetime. But generally, in a large number of cases, we may not be dealing with the newborn babies, right? Generally, we will not deal with the newborn babies. We may be dealing with people who have completed or who have attained some X years, and after X years, so probably we'll be dealing with individuals who are X years. So after, for an individual who is a 20-year-old, so for a 20-year-old person, what is the future lifetime? Or a 50-year-old person, what is the future lifetime? So we are talking about for X years person, meaning that a person has already lived. The person has already lived. The person has already lived. Sorry about that. The person has already lived up to X years. And for that person, we are interested in finding out the future lifetime. So that's why we changed the notation. For a newborn baby, we have represented the future lifetime as t. But for a person who has already attained age of X and who has survived up to the age of X, and I'm interested in finding out the future lifetime of a person, I will represent that as a random variable tx. Probably if it means, if I write it as t20, it is the random variable regarding the future lifetime of a person who has attained 20 years of age, or a 50-year-old. What is the future lifetime of that 50-year-old person? That is what we are representing as T50. So Tx is, in general, we are writing it as future lifetime. So this is the future lifetime of a person who has already attained the age of X, or who has survived up to X years, and within that x is between x this or and omega. So this x lies between 0 and omega. So in a way, if I'm talking about t0, it's nothing but the future lifetime of a person who is current age or who has attained an age of 0, which is nothing but a newborn baby. So just like as we have defined f of t, where we have said that probability that the lifetime is less or equal to t. The same logic, if I'm extending it to a person with age x, we are simply saying it as the probability that the future lifetime variable for this person is less or equal to t. Similarly, I can go with the survival function, which is 1 minus of f of fx of t, which can go as 1 minus the probability that the future lifetime of x is less or equal to t. Or probably it is as good as saying probability that tx is greater than t. So that is what is coming out as a survival function of a person whose current age is x, right? So now, if I have to write those things in a different form, let's say if I'm talking about fx of t. So what are we saying? That the person has already survived for x years, and we are trying to find out what is the probability that he will die within the next t years. Means that the other way of saying that, what is the probability that tx will be less than t or equal to t given given he has already survived for x years, right? So the other way of writing is the probability of the total lifetime less than x plus t, given that he has already survived for x years. So the other way to write this, if I'm looking at probability A given B, or A intersection B divided by the probability of B, that if I'm applying the same kind of concept here, A intersection B, which is nothing but f of x plus t minus f of x, and divided by the probability of t greater than x, which is nothing but the survival function s of x. So you could very well write fx of t, which is the future lifetime, the probability that a particular person who is age x, whose current age is x, who will die within the next t years, is what can be given as fx of t, which would work out to f of x plus t minus f of x divided by the survival function up to x. Now this is where the actual notations are coming into picture for the same. f of x of t, the actual notation for the same is coming out as tqx, which is nothing but the probability that a person currently aged x will die within the next t years. So if I'm saying tqx, I'm saying it's the same as fx of t, means that the probability that the person aged x currently will die within the next t years. Probably if I'm saying 1qx, it's nothing but the probability that the person currently aged x will die within the next 1 year before he attains the age of x plus 1, he is going to die. So 1qx is sometimes written as qx, and qx is nothing but the annual, because within the next 1 year that the chance that age x will die. So this is the annual rate of mortality. Similarly, for the survival function Sx of t, which there is a notation which is called Tpx. P is for the probability of survival and Q is for the probability of death. So what is the probability that the person aged X is going to be alive for at least the next 2 years, right? So that is what is the survival function. So this, it can also be 1 minus, so this I can also write it as 1 minus t qx. And again, the same logic when I'm saying the same logic if I'm saying 1 px, what is the probability that a person X will survive for at least 1 year? So that's again working out as an annual rate of survival rate itself. So that is one more notation we need to be comfortable with. Now the other concept in the same context of TQX, we also discuss another context which is called force of mortality. So this is another context which is what? Force of mortality. So here a slightly kind of aggressive mechanism is like when I'm using TQX, we said that the person aged X dying within the next 2 years. The person aged X dying within the person aged X dying within the next 1 year. Probably if I'm looking at QX and probably 0.001, a person aged X dying within a person aged X dying between 0.001 1 years. So that is what we are calling as, so this is what we call as the instantaneous force of mortality. So this is what we call the instantaneous force of mortality. So we are primarily looking at a very short point in time. So the probability that a person aged X is dying within the next H years, where H is a very, very small number. Where H is a very minute number, we talk about this particular number in case H is very, very small. We call it as the force of mortality, or sometimes the same is being referred to as the hazard rate, and that generally gets represented. So this gets represented with a new X presentation, so which goes with the probability that the person aged X is going to die in the immediate time frame. That is what we are going to talk about as mu X, and that's how the representation comes out as the probability that a person the future lifetime of a person is less than or equal to x plus h, given that it is greater than x. So, and I'm talking about, so here I'm talking about the limit h tends to 0. So here I'm doing, let me just write it properly. So this will be nu x, which is equal to the limit as h tends to 0, then 1 by h, and then the probability future lifetime is also equal to x plus t, given it's greater than x. So this is what we are calling as the instantaneous force of mortality or instantaneous measure of mortality. So probably if qx is talking of a number of, like a person aged x dying within 1 year, which is more in a discrete kind of a form. When I am more looking at the continuous form, I'm talking about nu x. So it is a continuous form, dying within the next moment. That is what we are calling as the instantaneous force of mortality. That is the reason when I'm thinking of hqx, h is very, very small quantity, much less than a year. We can even think of writing as h multiplying by nu x, because nu x is instantaneous. So h equal instantaneous period is what will give the hqx kind of a formula. So that's where when we talk about the probability of death within the next h period, where h is very, very small, we are talking about it's equivalent to the force of mortality multiplied by the h, which is that small time period. That is one more relationship, and that is one more understanding of the force of mortality that is required for us. So just updating a little bit, when I talk about nu x plus t, who has already survived up to the age x, right? For a newborn, that is the earlier definition, but for a person who has already survived up to the age x, I can very well write it as mu x plus t. Means that the probability that a person will die within the next t periods. So the probability that the person whose age is currently age x will die within the next t periods, or will survive up to t and die. So instantly when he attains between x plus t, he dies. So that is the probability I'm trying to understand. So that is why I call it as the limit, and then h tends to 0, then 1 by h, that the probability that so that is the probability that the time the probability that the future lifetime is less than or equal to x plus h plus t, given that he has already survived up to x plus t. Or the other way I can write it as limit h tends to 0, 1 by h, probability that tx less than or equal to t plus h, given that tx is greater than t. This is what is the definition of nu x plus t. The instantaneous probability that the person whose life is x has survived, has died exactly by the time he reaches x plus t years, right? Not within the next years, but he attains the age x plus t and exactly dies at that particular age. That is what is given by mu x plus t. So we need to understand, apart from the basic survival function and the basic probability distribution function of the future lifetime, we have to try to express those things in terms of actuarial notation or probability of death and survival, and how can I convert them into the instantaneous rates of death and survival using mu x and mu x plus t kind of notation. Now we will move further to understand the survival probability using the same kind of context. Now that we have talked about the probabilities of death, I can also look at understanding the probability of the survival. We have already defined for a person who's age x, so I can denote the probability of survival as x, Sx, which works out to be the probability that the future lifetime is greater than t. Or the other way, I can write this as the probability that he lives for more than x plus t years, given that he has already lived for more than x years. So if I look at the intersection between the two, greater than a given b, a intersection b, e greater than x plus t and t greater than x. So this comes out as t greater than x plus t itself. So this can work out as p t greater than x plus t divided by p greater than t. So this can work out as s of x plus t years, given that he has survived for t years, x years already. Okay, so he has survived for x years already. So this is what is coming out as a survival function, and of course the survival function of x. We have said Sx. I can very well note it as so it's the survival function of Sx. So I can very well notice as Tpx. So I write this Tpx as, because Tpx is a survival function for a person aged x surviving for the next t years. So this is working out as Sx of t itself. So Sx of t is working out as the same as Tpx, the probability that the person age x is alive for the next t years. So this also Sx plus t, I can very well write it as x plus t p 0. A newborn person surviving for x plus t years, and then I can write it as x p 0. New person surviving up to x years. So probably this is coming out that if I'm doing a simple verification part, it's coming out that x plus t p 0 is equal to xp0 multiplied by tpx, mean a probability a person age 0 surviving for the next x plus t years is the same as the probability for a person age 0 surviving for the next x years. So he survives for the next x years, so his age will become x, and then he's surviving for another t years. So in generally, if I have to very well write s plus t p x, it is nothing but, I can very well split it and say tpx, probability that a person aged x surviving for x plus t years is the same as the probability that a person who's aged x surviving for t years, and When he survives for t years, his age becomes x plus t. From there, he's surviving for the next s years. So that is the way I can very well express s plus t px. Or it could be the other way also. He could survive for the first s years, and by that time his age will become by x plus s, and from there he's surviving for the next t years. So this is one more important relationship we need to understand. So the probability that the person will survive for the next s plus t years is the same as he's surviving for the first s years, and then the probability for surviving for the next t years, or vice versa. So this is one more important relationship we should be comfortable with in terms of measuring the survival probability. Right? Apart from the probability of death, we are also interested in identifying the probability of survival using this kind of mechanism. Right? So once we are clear on this part, from the distributions till now we were looking at fx of t, which is the cumulative probability distribution of the future lifetime variable, and sx, which is the survival function. But now we'll slowly move towards the probability density function. Now our focus will move on to the probability density function of tx. So we are not looking from time zero, time period, or what is the distribution, or what is the probability that this particular years. I'm not looking at those aspects. We are more looking at the probability density function of tx, which we are representing as, so this is represented as small fx of t. So the distribution function is represented by the capital X, by the capital F xt, and the probability density function is denoted by the small fx of t. And if we use the derivative language, I can very well find the density. Taking the derivative of the distribution function, I can arrive at the density function, right? So you take the derivative of the distribution function to get the density function, and that is what we're trying to do here also. So fx of t is the density function, which I'll get by taking the derivative of fx distribution function of the future lifetime random variable, which is given by fxt. So let's see what this works out to by doing a little bit of calculations. So going ahead with the calculation of the probability density function fx of t, we are saying as d by dt fxt, capital F of x of t. So from there we know that capital fx of t is nothing but the probability that the probability of future lifetime of a person aged x is less than or equal to t. Or in another way, I could write it as the limit h tends to 0 1 by h probability of tx less than or equal to t less than or equal to t plus h given tx is greater than t. This is how we can write it. Now the same can continue as 1 by h, and then the probability of now I'm looking from a newborn baby perspective, t less than or equal to x plus t plus h given t is greater than x plus t, right? So divided by h. So here I can very well write this in the form of limits. So probably 1 by h just probability of t less than x plus t plus h given t greater than x plus t divided by h. So from this perspective I can look at it as I can express probability of let me redo the same. Let me redo the same again. So let me redo the same. I'm more interested in d over dt fx of t. So this is working out as d over dt probability of tx less tx less or equal to t. Now the definition of d over dt, or the derivative definition, if I'm looking at it, it is limit. So this is what limit h tends to 0 1 over h probability of tx is less than or equal to t plus h minus tx probability of tx. So probability of tx minus probability of tx less or equal to t divided by h. So this I could very well rewrite it as, if I'm looking at as limit h tends to 0 1 by h. So I expand this one, p the probability of t less than or equal to x plus t plus h given t is greater than x minus probability that t is less than or equal to x plus t given t greater than x. So this I can write. So this is fine now. Now I take each one separately. So I take it as limit h so only if I'm taking this part, probability of t less than or equal to x plus t plus h given t greater than x. So if I'm looking at this particular aspect, I can rewrite it saying probability of t less than or equal to x plus t plus h minus probability t less than or equal to x plus t divided by the survivor function t greater than x multiplied by h. So I can very well, so if I multiply the numerator and denominator by s x plus t. If I'm having that, and also divide by x plus t, I'll get as 1 by h into probability of t less than or equal to x plus t plus h minus p probability of t less or equal to x plus t divided by s x plus t. Yes, so I can write it as so this I can write it as mu x plus t. So the left hand side I can write it as, so this I can write it as sx of t, and this is coming out as and this I can write it as the notation of mu x plus t. So this is mu x plus t. So if we're looking at the density function, fx t, it is the same as d over dt fx. So this comes out as the survival function to the edge x, then mu x plus t, the instantaneous death at that particular point in time. So in short, if I have to talk about the probability density function fx over t, we say that the probability that the person age x is alive up to the age t, and by that time he will attain the age x plus t. What is the instantaneous rate of death at that particular age? That is what is typically being worked out as the probability density function, which is what is the probability that a person aged x will die exactly at t years from now. So that is what is working out as the density function. But when we talk about the distribution function, we are talking about the probability that the person age x will die within the next t years, right? All right. Now the same survival related probabilities, they also come from different life tables. Right, from the actual tables we see that there are life tables talking at some basis of 100,000. For every 100,000, when I'm talking about Lx born, Lx is talking about the number of lives alive population at age x. For every 100,000 people born, Lx is talking about what is the population that is alive whose age is x. Similarly, dx is talking about the number of deaths between x and x plus 1. So we can say our dx is equal to lx minus lx plus 1, and we know that dx is nothing but number of deaths during that particular period. So when I have to talk about px, the survival probability, we are talking about lx plus 1 divided by lx, number of people who are alive at x plus 1 divided by the number of people who are alive at x. but here we are mandatory taking our integer years itself. So if we're working with years less than integers, probably like what is the probability that a person aged will be alive for the next 6 months or 3 months for such kind of values we cannot get from the life tables. We may have to make some kind of assumption. We have to make some kind of assumptions, especially if we have to work for probabilities which do not involve the integer ages. So one kind of assumption, we assume that the deaths are uniform across the integer ages. Between the two integer ages, the deaths are uniform. Or we talk about force of mortality. We talk about force of mortality is constant. Force of mortality is constant in between the two integer periods. Or there is one more assumption called as Boussier assumption. Boussier assumption. So we say that that assumption will hold true, which will go with the simple mechanism that for a person aged x plus t, the probability that he dies within the next 1 minus t years, by the time he completes 1 year, is nothing but 1 minus t times qx. So this is the typical Barduzzi assumption. So we make some, so we allow these three forms of assumptions. What assumption we make at what stage, we will try to look at it slightly later. When we talk about the deaths are occurring uniformly in the integer ages, we could go with the relation that t qx is nothing but t qx, where t is less than or equal to 1. When I go with the Barduzzi assumption, I go with this kind of relationship. So any of these things will really make an impact in, especially depending on the assumptions we are taking with respect to the ages, or with respect to the pattern of death between the two integer years. The probabilities of death is going, or probability of survival are going to change a little bit in our calculations. And the next important concept that we are going to handle as a part of this session is whatever the rate of mortality we are talking of. Whatever the rate of mortality, we talked about it as TQX. The person aged X will die within the next T periods. Or the annual rate of mortality, QX, the probability that the person aged X is going to die within the next 1 year. So a person aged X will die within the next 1 year. By the time he reaches X plus 1, since we are beginning from the age X and going up to the age X plus 1, we are calling this rate of mortality as initial rate of mortality. because we are starting to observe the person exactly from the age X and going and looking at observing that person until he attains the age X plus 1. But on the other side, when I'm looking at the other definition of the rate of mortality, which I call it as a central rate of mortality. I don't define it by QX, but I define this by MX. And MX will come out to me as QX divided by over a period of 1 year for whatever the time period I'm observing, for whatever time period that party is alive. So that party should be alive. TPX dt. So this is what we are calling as the central rate of mortality, because we are talking about the probability of a person not starting at X and not dying up to 1 year. We are talking about the probability that the person will die somewhere between X and X plus 1, right? So for every person who is alive between X and X plus 1, this is what we are saying as TPX. For any person who is alive between X and X plus 1 years, what is the probability that he is going to die? Right? So this is, we are talking about the probability that the person is going to die between X and X plus 1 years, but every person who has been alive between X and X plus 1. So that is why the denominator, when I'm looking at this, it is not coming out as 1, because we may be observing that person only we may be observing that person only for a certain period of time. So we are talking about this particular time as the expected number of years, or the expected time that is spent between age X and X plus 1 by a life which is alive at the age X. So that is the reason why sometimes we will not take the initial rate of mortality. We depend on the MX, which is the central rate of mortality, and probably the way I express this the same is QX is nothing but the integral of 0 to 1. The person is alive up to the point T, and he is dying at the time X plus T. So the numerator, which is this one, is coming out as this one, and the denominator is working out as the probability that is alive for the next T period. So this is what is a better way to explain the central rate of mortality, and especially if I have to use it to project the number of deaths rather than using the initial rate of mortality, especially when I'm talking about the number of lives alive or the number of people who are alive in this particular age group. If I know that these are a number of people who are alive in the particular age group, and I'm trying to find out the mortality for that particular age group, I will depend on MX, which is the central rate of mortality, rather than the initial rate of mortality itself. So instead of saying, probably a better way to put it is, when I'm talking about initial rate, initial rate of mortality is like the number of deaths between the number x plus and x plus 1 divided by the number of lives alive at age x. When I'm talking about the central rate of mortality, the numerator is still the sum, the number of deaths between x and x plus 1, and probably here we're talking about the total time spent alive. So if a particular observation is censored during a particular period, or rather than considering the number of lives at the beginning, I'm going with a central rate of mortality. We are talking about the total time spent during this particular period. So that is what is the major difference. We are more looking at the estimation of mx. When I'm talking of qx mu x plus t, we are talking about mu x being a constant between the edges of x and x plus 1. So we can very well link mx to some extent with nu. So that is one kind of important relationship that we're trying to build between mx, qx, and mu-x. Right? So we need to understand the typical relationship that is existing between these three, so that we can convert this from one form to another at any point in time. So that is the basic understanding of the future lifetime or the random variable. Now we go into a few calculations. Associated with the future lifetime variable, where we'll be interested in to compute the expected value of the future lifetime. So it's the future expected value of the future lifetime. So let's get into the calculations of the expected value of the future lifetime random variable. So to compute the expected future lifetime value for a person who has lived up to the age x, so instead of looking at the random variable tx, now I'm interested in finding out the expected value of this random variable. So I call it as the expected value of tx, means from x. On an average, how many years is this person going to be alive? On an average, how many more years is this person going to be alive? That is what we are calling as the expected value of tx, or otherwise we denote it by ex with the circle on the top. Otherwise we try to pronounce it as e circle x, means expected number of years, expected future lifetime of a person who is aged x, right? So here we'll try to see if I have to understand the expected lifetime for a person. We know that from the age x, what is the probability that he is going to be alive, let's say from 0 to the omega minus x years, because at the max you can be alive up to bigger years. So what is the probability that the person will be alive, will be alive for at age x plus t? So this is going to be something like this. What is the probability that the person will be will be dying at the age x plus t, x plus 1, x plus t plus 2, and so on? That is the reason we are integrating this particular probability multiplied by t. For any expected value, we multiply the value with its probability. The probability that the person will be alive for t years, right? The probability that the person will be dying at t years the probability that the person will be dying at t years, we say it's tp x nu x plus t. So when I'm trying to find out the average age, average lifetime, I'm multiplying by the weighted average, which is the t. So this is the overall lifetime I'm going to get. So if I have to simplify this, I can look at it as tpx nu x plus t. I can write it as fx, which is the density function with respect to t, which is nothing but the derivative of capital Fx of t, which we can write it as the derivative of capital Fx of t, tqx, and this tqx I can write it as 1 minus tpx. So the derivative of this is becoming as over tpx. So that is what I'll try to write here. Instead of tpx nu x plus t, I will write it as a circle x. I'll write it as the integral between 0 and 1 omega minus x t into minus gerund of t tpx. Now I take the integration by parts. So using the integration by parts, the right hand side so it is directly the integrity. So this comes out as a t px omega minus 0 x. So using by parts, you get this 0 to omega minus x, the derivative of 1 multiplied by tpx. So this becomes as tpx dx. So between 0 and omega minus x, the probability of survival, when I'm looking at this and this, the total probability of survival, the person is going to die. So this is directly working out to 0 plus 0 to omega minus x tpx dx. So the expected future lifetime of a person aged x, I can simplify it as 0 to omega minus x tpx dx. So sometimes we may not know the omega, so I'll take it as 0 to infinity, infinite, and then t p x dx. So this is, I don't need, so this is how it comes out. So the expected future lifetime for a person aged x, I can take it as tpx, integrating this tpx over 0 to infinite, right? Similarly, when I'm looking at the variance of the future lifetime, the variance of the future lifetime random variable, the same integration will happen between 0 to omega minus x. I'll take tpx nu x plus t, the probability that the person dies at a particular age x. Then I multiply this with t squared. So this is what will give me the variance associated with the future lifetime random variable. Or this is the expected value. So we define variance as expected value of x squared minus expected value of x whole squared. So expected value x squared is this one, minus expected value of x, so minus e equal x. So this will give me the variance of t of x. So that is the variance of the expected future lifetime, and the variance that I'm associating with the future lifetime of a random variable for a person whose current age is x. But on the other side, for simplification dimension, apart from the future expected lifetime, we also have a simplified version of called the quartet expected lifetime. The full expected lifetime is what we define as tx, as a random variable, so which is measuring to exact value. But if I take only the integer part of it, let's say let's say the expected lifetime of a person is 30.4 years. So if I take it only as 30, even if it is 30.8 years, if I take only the integer part of it, like the rounded down finger of the integer part only, we call that as the quartet future lifetime. So the quartet future lifetime is always the number of years in an integer life. When I'm talking about the future lifetime in general, we are looking at it as the exact number of years, even the rounded portion of it. So that is the reason the quartet lifetime is represented by kx, which is nothing but the bracketed value of tx, which is the rounded value of tx. So kx here will only take either you'll be alive for 0 years, 1 year, 2 years, and so on. The future lifetime are either 0, 1, 2, and so on, but they cannot be continued. So that's why when I'm talking about the probability that kx will take any one of these values, let's say kx is equal to some small k, which is the other 2 or something. So we are saying that this is equivalent to the probability that the person aged X will be alive for that K years, and by that time he attains the age X plus K, and the probability that he dies and the probability that he dies at X plus K. So from a typical cadet expectation perspective, I'm looking at only the integers, whereas if I'm looking at the full expectation or full lifetime, I'm looking at the decimal parts also. So even the same, if it goes with the expectation, I will not write it with a circle. So this is nothing but E of X, which is nothing but the expected value of the cadet. Lifetime random variable E of Kx, which actually comes out as simple summation. In a cadet form, it's not integration. It's coming out to a summation K is equal to 1 and omega minus X K P X. So in a continuous form, we are integrating 0 and omega minus X in this continuous form. T P X P. Whereas in a cadet form, we are summing between 1 and omega minus X, the kpx. Both of them can be represented or related in this particular manner. The same way when I'm going ahead with the variance associated with the cadet lifetime, variance of Kx, which again goes with a similar kind of notation, where I'm taking the summation is equal to K is equal to 0 to omega minus X Kpx Qx plus K, multiplying this by K squared minus X minus expectation of Ex squared. So this is what is giving me the variance with respect to this random variable. Right. Then we are now trying to see how do I relate the future expected lifetime, which is the complete so it's the complete expected lifetime, and also Ex, which I'm taking as the cadet expected. So so on an average, the relation is E circle X is somewhere equal to X plus 1 by 2. So this is a typical kind of relationship we are bringing in between complete expected lifetime of a random variable whose age is X versus a cadet expected lifetime for the random variable. Now, a couple of important things just to look at. We said if I want to know the formula of T Qx, so we said this is fx of t, and how do I write this fx of t? So I can write it as integral 0 to t the density function fx of s ds. And what is the formula for fx of s? A person whose age is x, let him survive until s, and there he dies. x plus s. So whenever I'm interested in finding out the TQX, we are saying we are looking at first the person being alive up to the age s, and but he will attain the age x plus s at that time. So immediately he attains the age x plus s within that small period of time. By the time he attains x plus s, the probability that he is dying, that is why we are using the instantaneous force of mortality here. So the s could be any number. So that is why we are integrating between 0 to t. All possible values of s could come out. So he is alive until that time and he is dying up to x plus s. So for all those things is what we are. So for all those things is what the probability of dying between 0 and t years, right? Anywhere from now to t years or to t years from now, the probability that the person is going to die. So we're trying to see that what is the probability that the person is going to die at every instant from now, from every instant from 0 years to t years from now, given that he is being alive at that point in time and then dying at that particular small interval of time. So this is how we can express the TQX. But when I'm looking at TPX comes out as 1 minus TQX. The other way we have seen some time back, this is going to come out when we are trying out the typical PEX formula. It's coming out to be 1 minus TQX. Or in another way, when we looked at in another way, when I look at the TPX, we have seen slightly earlier the relationship relating to TPX slightly earlier when we computed. I know that capital Fx of t is nothing but integral 0 to t small fx of t small fx of ds. So the typical TPX nu x plus t, which is so the typical nu x plus t, so this is fx, this is fx t is equal to TPX nu x plus t. So I can write this as the gerund over gerund of t, capital F x t, and then this I write it as gerund over gerund of t, 1 minus TPX. So this I write it as the gerund over gerund of t, TPX. So basically I'm finding out the relation saying minus gerund over gerund of t, TPX is equal to TPX nu x plus t. This is the relation. So this is the relation that I have. So I'm going to make a small modification by bringing the TPX down. So this becomes gerund over gerund of t. TPX. You divide this by TPX. So this turns out to be nu x plus t. So this is nothing but the derived over derived of t, then the log of t px, because yes, I can write it as this because the derived over the derived of t in x is nothing but 1 over x, then the derived over derived of t. We're taking it as 1 over x into in x. So this is what I'm taking. So if I'm taking as the derived of in x, I'm taking it as what? I'm taking the, so this turns out to be, 1 second. So I'm taking, let me write it again. So this is derived over derived of t, then in x. So this turns out to be 1 over x. So referring to this, taking the derivative of this, and that's why I'm calling it as the derived over derived of t, tpx, with the minus sign. So this is coming out as nu x plus t. A little bit of more work will give me, so this will give me as the n tpx. So if I take integration of both the sides, and if I take the negative to the right hand side, so log tpx, it is becoming the integral of minus nu x plus t. And if I'm taking out the log also, so this comes out as tpx is equal to e to the power minus integral 0 to t nu x plus t. This is how I'm defining the tpx from this particular relation. I'm talking about tpx is nothing but e to the power integral 0 to t nu x plus s ds. So this is the simple way we can define the tpx, and tqx, we have defined it primarily. So tqx, so we can say tqx gets defined as the integral 0 to t, a person being alive for the age x, and then from there he immediately dies at the age of x plus s. Yes, so these are the two important formulas we need to be comfortable with expressing the probability of death within the next years, or the probability of being alive within the next years, in the forms of the probability density function and instantaneous rates of probabilities of rates over the period. So these are the things that you need to be comfortable with, and from there, once we are comfortable with those kind of formulas, I am looking at the survival formulas, right? Some other important survival probabilities or formulas. So survival formulas. So here we'll be using what? The parameters. So I'll look at now for using parameters. So some of the survival formulas. Now that we know that the survival function or probability of surviving, which is what TPX, right? The probability of survival, which is SXT, the same as TPX. So this is going to be e to the power of minus of integral 0 to t nu x plus s ds, right? Here I would like to make a few assumptions. So if nu is constant, if the hazard rate is constant, right, I'm talking about nu x at any point is equal to nu x. So the nu x plus s does not keep changing with x plus s during the entire period. If I'm assuming that the hazard rate is going to be constant, then I can very well improvise this TPX as e to the power the integral 0 to t nu ds. So this works out to e to the power of minus nu s integrated between t to 0. So this will work out to e to the power minus nu t. So TPX, in case the hazard rate is constant, TPX between 0 and t, I can very well write the probability of survival for a person aged x for the next t period is nothing but e to the power negative nu t. So this kind of a model wherein we are assuming that the hazard rate is constant during the entire period, we call this kind of model, this is called the exponential. So in case of the exponential model, the survival function x of t, I can give it as e to the power minus nu t. Right. Now, a slightly different variant. In case sx of t, instead of being e to the power nu t, if I take it as e to the power minus alpha t the power beta, a slightly parameterized formula, t is still, instead of taking a constant, I'm taking a constant multiplied by parameter value. So this is called, whenever I see the survival function not as e to the power of minus nu t, but it is of this form, alpha t to the power beta, then we call these kind of models as the Weibull models. So let's see what we mean by this. So Sx of t. So S of t is given as TPX not as e to the power minus ut, but it comes out as e to the power minus alpha t to the power beta. Now we know that the survival function is nothing but probably I can write the survival function as 1 minus the probability distribution function x of t, and based on the earlier calculations we have also defined sx of t as e to the power of minus of integral 0 to 2t nu x plus s ds. Now working backwards, we have the log sx of t will work out to me as minus integral 0 to t nu x plus s ds. Taking the derivative, I get d by dt, the log of sx of t. So I take so this is going to be nu x plus t, nu x plus t in this case. So I can very well go with the nu x plus t, which is so I always take it as the gerund over gerund of t in sx. Now I know that sx of t, in case of a Weibull distribution, so in case of the Weibull distribution, this is gerund over gerund of t in dot e to the power minus alpha t. So log and e going out, so this is becoming as gerund over gerund of t minus alpha t to the power beta. So this is working out to so when I'm taking the derivative, so this is working out to the minus alpha alpha beta, and then t to the power beta minus 1. So that is what is coming out as the hazard function. So this is how it is coming out. Yes, so this is how it is coming out. If you take out the derivative, yeah. So when I'm taking the hazard function, so in case of the exponential model, so in case of the exponential function, nu x plus t is constant, so you take it as nu. So in a wavy model, I'm expecting the model that the hazard function is nothing alpha beta to the power t beta minus 1. And just for the understanding, if beta was assumed to be 1, we get nu x plus t, we get it as alpha, which is a constant value. So when beta is equal to 1, we will find that the Weibull model, so it goes to an exponential. When beta is equal to 1, the Weibull function goes to the exponential function, and what we could see that in this hazard rate, for this hazard rate, nu x plus t is equal to alpha beta t to the power beta minus 1. If if beta is or depending on the values of beta, whether it is, you find that if you find that if t is increasing, then the hazard function is also increasing depending on the value of beta. I can see the hazard function to be increasing or decreasing, or the hazard could be a constant, because the moment we see that beta is more and more is 1, then we see that it's an increasing function. If beta is less than 1, then we see that the hazard function could be decreasing kind of function. Within that framework, within the same framework, we could see that the hazard could be either increasing or decreasing depending on the value of beta. So different kinds of distribution can be very well created using this particular generalized form of variable models. So we can talk about the exponential model, variable model, and then we can look at the modeling of hazard rates, as well as we can look at the modeling of as well as the survival function. So in case of exponential function, we have seen that the survival function will go as e. So in case of survival function, we see that it goes to the power e to the power nu t. And in case of the variable model, the survival function will go to the power e minus alpha t power beta. In case of the exponential model, the hazard rate is constant. Whereas in the case of variable models, the hazard rate goes as alpha, beta, t to the power beta minus 1. So depending on the value of beta, the hazard function could be either increasing or a decreasing function, or even a constant hazard kind of a function, right? And from there, the one more aspect which I'm now interested in looking at is the loss of mortality. So I'm looking at the Gompers and Mackenham. So here we look at the constant. So this is associated with the exponential. So here we have seen that alpha, beta, t, beta minus 1 is associated to a Weibull model. So we see other functions as well in this Gompers and Mackenham laws of mortality. So now when I follow the other law, which is the Gompers law, so here I assume that the hazard function mu x will follow an equation bc to the power x. If the hazard function follows alpha beta t to the power beta minus 1, where t is the time period coming to period, we call it as the Weibull distribution. Whereas when I'm looking at the Gompers, I'm saying the hazard function ux is of the function bc to the power x. Generally, this is again an exponential function itself. We'll see how it works out as an exponential function, and it is generally used in the real world for middle edges. So this is used for the middle edges. The hazard function is a proper kind of fit for middle edges and order edges kind of scenarios. the way I could look at this particular scenario in this case, if I have to go with the survival calculations TPX, how do I go about it? It is known that TPX is nothing but e to the power of minus 0 to t mu x plus s ds. Going with the same concept, e to the power minus 0 to t b c to the power x plus s ds. Correct? So here I could very well write it bc to the power x plus s ds. You could write it as e to the power of e to the power negative 0 to t. I take out b c to the power x into c to the power s ds. So if I'm looking at the simplification, I'll take out the constant b c to the power x, integral of 0 to t cfs tcs, which is nothing but c to the power s, c to the power s. So this is nothing but c to the power s over log c integrated between t and 0. So this is working out as e to the power minus b c power x, and this is working out c to the power t minus c to the power 0, which is 1. So overall I can write it as e to the power of minus b by c to the power ax into c to the power t minus 1. In a simplified form, if I'm assuming that this entire thing is some g, so I'm writing as g to the power of c to the power x to the power c t minus 1. This is what will be the survival probability when I'm using Egg-Gomper's law, where I'm making an assumption that g is equal to the minus b over log c. So this is one kind of relationship what we can think of. More common application in respect to the hazard function. So that if the hazard function is uniform hazard rate across the period, constant hazard rate across the period, then I can look at it as an exponential distribution. Otherwise, I can look at the variables for some of them. Gompers, I can look at an exponential kind of mechanism wherein I can calculate the survival probability using this, and even if I'm looking at the two parameters, which one? This one, yes. If I'm looking at these two parameters, b and c. So in real world, if I'm having two different hazard function, nu x, or the force or mortalities at two different edges, I can very well try to get my b and c parameters out of them, right? So this is one thing. Similarly, if I'm looking at Markov law, so let's look at the Markov law. So let's look at the Markov law. So here we are looking at the hazard rate slightly, an improvisation over the Gompers. So here I'm adding a constant to the b to the power cx. The reason being the bc power x is more, so the bc the BC to power x is more appropriate for the order and middle edges. But in respective of edge, I'm bringing an additional value which is a constant, which is generally looked at with respect to accidental death. Accidental death. So these may not have any kind of resemblance with the edge. So they are irrespective of the edge. So looking at those kind of accidental deaths, we can model that as a part of the Maycomb law. So if I have to look at the survival probability, so the instant hazard rate, in case of the Maycomb law, I'm looking at this. So for modeling the normal along with the accidental death, so in this case, if I have to work out, this becomes e to the power minus 0 to t, and then you have mu x plus s ds. So we can write it as e to the power minus 0 to t a plus b c power x plus s ds. So this, we can take out e to the power minus 0 to t a plus b c power x into the power c to the power s ds. So let's break this off. You got e to the power minus 0 to t a ds plus so the minus goes out, integral 0 to t bc power x is constant, so I take it as c s ds. So the first one is working out to be e to the power of minus a t. So the first one is working as at plus bc power x into c power t over log c power t minus 1, which we have done like exact earlier. So this is what is coming out in case of the Maycomb mechanism. So that is where probably I can look at it as e to the power minus at, then plus bc. Maybe I'll just take the multiplication root now. E to the power minus b over in c to the power x, and then ct minus 1. So this part now become g, as we did earlier. So this coming out as g to the power c x, then ct minus 1. Right? And e power minus a, if I'm taking as some s, e power minus a, so this will be s power t. So if this is denoted by s, then it comes out like that. So this is how it's coming out of the probability of survival in the case of the Maycomb equation. So this is the way we are finally looking at 4 different variants with respect to the survival probability, the hazard rate. So the hazard rate, so if it is constant, we call it as exponential kind of a model. So if it's constant, we call it as the exponential kind of a model. If it follows alpha, beta, t, beta minus 1, we call it as the Weibull model, which can be exponential. So this can be equal to exponential if beta is equal to 1. Or b c power x, we call it as the Gompers model. So we can also say a plus b c to the power x. We're equating it to the Maycomb model. And if as I'm discussing these 4 models, we are interested in finding out the survival probabilities. The survival probabilities, which is what TPX. Which is what TPX. And just one more important finally is we generalize the Gompers and the Maycomb as what we call as the Gompers Maycomb family. So we generalize this as the Gompers family. Instead of taking a constant here, we talk about a polynomial. So here we talk about a polynomial as a function of t plus an exponent polynomial 2 as a function of t. So in this case, we are talking about bc power x. I could have written as e to the power in b, bc power x. This can be converted to an exponential form, so which is nothing but e to the power in bc to the power x. E power log bc is what is working out to be the same. So in another way, it is working out as so we are saying polynomial. I could very well write it as e to the power in b plus x in c. So in a way, it is becoming e to the power in b plus x in c, which is nothing but a polynomial of order 1. So it's a polynomial of degree of 1, whereas a is becoming a polynomial of degree 0. So in general, when we are talking about the Gompers family for the hazard rates, so in general we are writing them in the order of GM R, S, where R is the degree associated with the polynomial 1, and S is the degree associated with polynomial 2. So the general Maycomb family is what is coming out as the Gompers Maycomb. So this is what is coming out as 0, 1. So the first one is a constant, and the second one is of order x, which is the degree 1. So in general, I can create any such kind of hazard-based models, wherein the polynomial one could be of degree r, and of polynomial 2 could be of degree s. So this is what in general the coverage of this particular session. Initially we started off as a quiz, so just as a quick summary to work out. Initially we looked at from a mortality survival model creation perspective. So we have looked at the basic definitions of the probability of death and the probability of survival. So we define f of we initially defined t of and t of x, which are the random variable associated with the future lifetime, and based on we arrived on f of t and fx of t, which are associated with the probabilities of death for a newborn, and for a person aged x, and corresponding survival probabilities taken as x of t. Then we have got into the definition, the actual definitions of t, qx, and qx. Within the next t periods, t, px, and px, the person that the age x is going to survive for 1 year, another t years, or etc, etc. And the most important formula of s plus t px can be written as spx, and then he's going to attend x plus s, and he's surviving for 10 more years. And we also look at the formulas, linkage between the force of mortality, which is more of the instantaneous kind of measure, force of mortality, to the rate of mortality. So this is a kind of like a discrete kind of measure, versus Q. So we have looked at this one and this one. We have looked at the life tables and how to extract information from the life tables. And then we focused on the relationship between the central rate of mortality, denoted by mx, and try to in respect to qx. Then we have also looked at the expected value. I've looked at the expected value and the variance of the complete lifetime, as well as the curtailed lifetime, the integer version of the random variable. So we looked at computing the expected value of the variance and the expected value and the variance of the complete and the curtailed lifetimes. And then at the same time we try to find the relationship between the complete expected lifetime versus expected lifetime, curtailed expected lifetime. Then we have got into the relation in an integral form. How do I find out the integral form of the TQX and TPX. And finally, we looked at depending on some kind of assumptions about the hazard rate. We have talked about the exponential model. What is the survival probability with respect to that model? We looked at the Weibull model. What is the hazard rate and what is the survival probability associated with the Weibull? Then the Gompertz, then the Maycombs, and finally the general Gompertz-Maycomb law. So finally, that's what we have looked at, and as we have covered a lot, in this session, and I hope you understand and go through everything of the survival models and the parametric based. So we come to the end of the session. I hope you go through the video. See you in the next session. Thank you so much.